Hello everyone, and welcome to our presentation of TCC-Det temporally consistent cues for weakly-supervised 3D detection presented by Skvrna and Lukas Neumann from CTU Prague. Before diving into our motivation and methods, we'd like to give you a brief overview of what's coming up in this video. We present a novel approach for training weakly-supervised 3D detectors without relying on domain-specific human annotations. A key innovation is leveraging temporal consistency across adjacent frames to aggregate additional information. We also introduce the template fitting loss and appearance mask loss. Our method not only achieves state-of-the-art performance in weak supervision without human labels, but also delivers comparable results to fully supervised methods, with only a 0.7 intersection of a union 3D average precision gap, and matches fully supervised performance using just 10% of the ground truth labels. Let's begin with the motivation. One major challenge in autonomous driving is the high cost of obtaining precise 3D labels, with labeling a single object taking up to 100 seconds. This results in small, region-specific datasets. However, for vehicles to operate safely, they must be able to respond to rare and unpredictable situations, which are often not represented in such limited datasets. Now, let's move on to the entire pipeline. First, focus on the grey rectangle on the left, which represents the unmodified voxel CNN 3D detector. The input is a LiDAR point cloud, processed by the two-stage detector to output 3D bounding boxes. In this pipeline, the loss is calculated between the predictions and pseudo-ground truth, whereas in the original version, human-labeled ground truth is used. We'll explain how to generate the pseudo-ground truth later. Initially, only the grey portion is used for pretraining, as it's significantly faster. After pretraining, we employ the template fitting loss and appearance mask loss during fine-tuning. Mask CNN is applied to images from multiple adjacent frames to generate 2D instance masks for each car. We then extract corresponding points by projecting them onto the image, resulting in a point representation for each mask. To aggregate this information across frames, we first classify whether the car is stationary or moving. For stationary cars, points are aggregated directly across adjacent frames. For moving cars, we estimate their trajectory, allowing us to derive an accurate yaw angle. Finally, to generate 3D bounding boxes that serve as pseudo-ground truth, we apply direct fitting of a template car model. Please note that we do not use any 2D or 3D labels from the dataset we are training on. Now that we've covered pseudo-ground truth generation, which is essential for pre-training, we can dive into the additional losses used during the network's fine-tuning. The template fitting loss, visualized in the top right corner, ensures that the predicted bounding box, replaced by a template model, aligns with the aggregated points. The mask appearance loss ensures that the predicted bounding box, once replaced by the template, matches the predicted mask in 4 steps. Obtain the prediction, replace it with the template mesh, render the mesh, and compute the binary cross-entropy with the math from mask CNN. During our research, we discovered that despite the variety in car types, shapes, and dimensions, using just 4 template models, sedan, SUV, MPV, and hatchback is sufficient to generalize across all car models. We speculate this is due to the fact that the lower half of most cars is quite similar, while the top half, though varying, still follows certain predefined shapes. Our evaluation starts with the kitted dataset, as it is the only dataset that allows us to make relevant comparisons with other methods. We have divided the methods into 3 distinct groups. The first group consists of fully supervised methods, which rely entirely on human annotations. The second group includes weakly supervised methods that use some subset of human labels, whether 2D annotations or a small subset of 3D annotations. The third group encompasses weakly supervised methods that use no human annotations at all. This is where our method falls. We can clearly see that we hold state-of-the-art performance in the third category, achieving results comparable to the second category and significantly narrowing the gap to the first category. We are the first weakly supervised method to evaluate in the Waymo open dataset. Our results show that we achieve competitive performance, particularly at 0.5 intersection of a union. One of the main limitations of our method is that we cannot label cars that are outside the field of view of the cameras mounted in the vehicle. While aggregating points can help us label cars outside the field of view, this is only effective for stationary cars. However, mounting additional cameras is a relatively inexpensive solution, isn't it? Thank you for your attention. The code is freely available on GitHub, accessible via the QR code at the bottom. You'll find 2 examples of our method applied to the kitty dataset. In green are the human ground truth labels, and in red are our predictions.